Hey guys, I'm Jay. Today is my LeetCode review one-take vlog on the 98th problem. Validate binary search tree. We are given the root of a binary tree and we'll determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key, and the right subtree of a node contains only nodes with keys greater than the node's key. And both the left and right subtrees must also be binary search tree. And let's see example 1 here. So the left child node's value is 1, which is less than the value of the root node 2. And the root node's value 2 is less than the value of the right subtree node 3. So this is a binary search tree. And for example 2 here, the root node's value is 5, but its right child's value is 4. So this fact breaks the property of binary search tree. So the output is false. Then let's get into our intuition to solve the problem. First, we need to know that an in-order traversal of a binary search tree will produce values in increasing order, such as 1, 2, 3, and so on. So we can implement an in-order traversal to check validity by comparing each node's value with the previous node, such as iterative in-order traversal, recursive in-order traversal, or Morris in-order traversal. And we can also do a recursive bounds checking. When we traverse the tree in pre-order traversal, we can pass down the lower and upper bounds for each node. When we move to the left subtree, we'll update the upper bound. And when we move to the right subtree, we'll update the lower bound. And if a node's value is not in its value range, the tree is not a binary search tree. Then let's get into our first solution. Recursive bounds checking with pre-order traversal. Recursive bounds checking. First, we'll declare and implement a new method called isValid binary search tree. Private boolean and isValid binary search tree with 3 variables. First is the tree node. Second is the lower bound, integer lower bound. And the third one is the upper bound. And inside the method body, in the first state, we'll handle a bad case. If node equals null, there's nothing to check, so we'll return true. Then we'll check if there is a lower bound. If so, we'll compare the lower bound and the node's value. Integer value equals node.value. Then we'll check if lower bound is not equal to null and if node's value is less than or equal to lower bound, which means it breaks the property of binary search tree, so we'll return false. Similarly, we'll compare the upper bound and the node's value. If upper bound is not equal to null and value is greater than or equal to the upper bound, we'll also return false. Then we'll recursively validate the right subtree, and the node and the current node's value will become the new lower bound. If not logical symbol, recursively call the isValid binary search tree with 3 new variables, node.right, and the node's value will become the new lower bound and the original upper bound. If so, we'll return false. Then we'll cursively check the left subtree. If not logical symbol is valid, binary search tree with node on the left and original lower bound and the new upper bound, which is the value. Then we'll return false. And after auto check, if both subtrees are valid, so the current subtree is valid, we'll return true. Then we'll implement the first method here. We just recursively call the isValid binary search tree method. Return isValid binary search tree with root node. And there is no lower bound or upper bound here. So we'll pass to null. Then let's submit the code and check the correctness. Then we'll analyze the time and space complexity. Yes, our code got accepted. So the time complexity, it is big O of n, as we visited each node for only one time. And the space complexity, it is big O of h, due to the recursively call stack, where h is the height of the binary tree. And in the worst case, the space complexity would become big O of n for a skewed tree. And this is the first solution. Then let's get into the second solution. Iterative in order traversal. At the very beginning, we'll declare a stack to simulate the recursion for in-order traversal. Stack of tree node. Let's call it stack, and the stack variable is assigned to a new empty stack instance. New stack here. Then we'll declare a current variable. Tree node current, starting at the root node. Then we'll declare a previous node to store the previous node's value in order traversal. Integer previous, starting at null. Then we'll implement a while loop to traverse the binary tree, while current is not equal to null, or stack is not empty. If so, we'll continue the while loop. And inside while loop, first, we'll reach the leftmost node of the current subtree, while current is not equal to null. And inside the inner while loop, first, we'll push the node into the stack. Then we'll update the current node. Current equals current dot left. And out of the inner while loop, then we'll process the node on the top of the stack. Current equals stack.pop. Next, we'll check if the current node's value is greater than the previous value or not. If previous is not equal to null, then we'll compare each other. Current dot value is less than or equal to previous. If so, it breaks the property of a binary search tree, so we'll return false. After the check, we'll update the previous variable to the current node's value to prepare for the next check. Previous is assigned to the current dot value. Then we'll move to the right subtree current equals current dot right. And out of the while loop, which means we have checked all the nodes. So we'll return true, and it is a valid binary search tree. Then we'll analyze the time and space complexity. And the time complexity, it is also big of n, as each node is visited once. Oops, there's something wrong here. Current is spelled wrong. So the time complexity, it is big of n, and the space complexity, it is also big of h. Big of n and big of h, as the stack size can go up to the height of the tree, and in the worst case, if the tree is a skewed tree, the space complexity would become big O of n. And then let's get into the final solution, Morris in-order traversal. Morris in-order traversal. So the idea of the Morris in-order traversal is creating a temporary right pointer for a node's in-order predecessor back to the node itself to backtrack without a stack or recursion. And when we traverse the nodes, we'll check if each node's value is greater than the previous node. Then let's get started. First, we'll declare several variables. Let's say integer previous, starting at now. And we'll declare a current tree node, starting at root node. Then we'll implement a while loop to traverse the tree while current is not equal to now. We'll continue the while loop. And inside the while loop, first we'll check if there is left child or not. If current dot left is equal to now. If so, we'll process the current node. And the code is, we'll check if the current node's value is greater than the previous value. If previous is not equal to now, and current dot value is less than or equal to previous. If so, we'll return false, as it breaks the property of binary search tree. And then we'll update the previous variable with the current node's value to prepare for the next comparison. Previous is assigned to current dot value. Then, if the current node has real right subtree, so we'll move to the right subtree to continue the traversal. Or if the current node needs to backtrack to the next in-order node by temporal link. And the code is current equals current dot right. And this is the first solution. So the second solution is if the current dot left is not equal to now. And inside this method body, first we'll check if a left child exists or not. If so, we'll find the in-order predecessor of the current node, which is the rightmost node in the left subtree. The code is tree node with predecessor, starting at current dot left. Then we'll create an inner while loop to find the in-order predecessor. While predecessor the right is not equal to now, and predecessor dot right is not equal to current, to avoid endless loop. If so, we'll update the predecessor with the new value of predecessor dot right. Predecessor is assigned to predecessor dot right. And out of the while in a while loop, then we'll check if the temporal link does not exist or not. If predecessor dot right is equal to null, which means this is our first time to visit this node. So we'll establish a temporal link to the current node. So we can backtrack when we visit this node at the second time. Predecessor the right is assigned to the current. Then we'll move the current node to its left child to continue the traversal. Current is assigned to current dot left. And on the other side, if the predecessor do have a right subtree, which means the temporal link already exists and the left subtree has been processed. So we need to remove the temporal link and process the node. First, we'll move the predecessor dot right is assigned to null to avoid endless loop. And then we'll process the current node, which is we'll compare the value of the previous value and the current value. If previous variable is not equal to null and current that value is less than or equal to previous, then we'll return false. And after the check, we'll update the previous variable with the current node's value to prepare for the next comparison. Previous variable is assigned to current dot right. Oops, is current dot value. Then we'll move the current to its right subtree. Current is assigned to current dot right subtree. And out of the outer while loop, which means we have passed all the check, and this tree is a valid binary search tree, so we'll return false. Then let's submit code and check the correctness. Next, oops, there is something wrong here. Tree node. Let me check. Tree node is here. Then we'll analyze the time and space complexity. So the time complexity, oops, the correct variable is spelled wrong. The time complexity, it is big O of n, because each node is visited at most twice. Once when we establish the temporal link, and the second time is when we remove the temporal link. Yes, our code got accepted. Time complexity, it is big O of n, and space complexity, it is the best, which is big O of 1. This is because we don't need any recursive stack or explicit stack. And this is the end of my LeetCode review one-take vlog on the validate binary search tree problem. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, intuition and main idea, and detailed solution with very detailed annotations and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains the code and notes to build this online GitHub page. And thank you guys for your watching. I'll see you next time. Bye bye. And I'll put those two links on my YouTube description below. And see you next time. Bye.